In this session, we are going to talk about the credit grades, which is a very good alternative to the Merton model approach for finding out the probability of default. This is also a kind of a structural model. So we have Merton model as well as credit grades as widely used structural models. So here the only difference is the default, which in case of Merton model, we have said that the asset value at time t, where t is the maturity of the loan or the debt of the company, is lesser than the value of the liabilities at that particular point. Whereas here in the credit rates, the model says the default will occur if the asset value of the firm is lesser than some random barrier. Right? There is a random barrier. We'll talk about what it is. But if the asset value is lesser than some random barrier, that is when we say that the default is occurring. Right? The reason being, see, generally I can't expect that the firm will default only at time t. And we actually don't know the liabilities until the default occurs. Because even if you see, the company liabilities are available only as a part of their quarterly statements or annual reports, and they are updated only in a minimum of a quarter. Whereas the default can occur not just on the time period t, but it can actually occur at any point in time. So that is the reason the credit grades is a kind of improvisation over the existing Merton model. So if I am looking at the value of the asset today being some A, I am assuming that these assets will follow a log normal distribution just like a Merton model, and we are setting some kind of random barrier. We are setting it as some lambda times d. This is the random barrier that we are setting. So here the thing is, we are going everything on a per share basis. So A, the asset value also I am taking it as per share. The random barrier lambda d, where d is the debt per share, and this is what is the credit grade model specify. And lambda is more to do with the uncertainty in the recovery value, right? So that is the level of uncertainty in the recovery value, and it's not a constant, it's a kind of a random variable. Even what is being assumed is, even this lambda will follow a log normal distribution with a mean probably lambda bar and a standard deviation of probably some sigma, right? The mean, or yeah, the mean is some lambda bar and a standard deviation of some sigma. So based on that, just like in a Merton model, we are going ahead with finding out what is the asset value at the current period, what is the volatility. Oh, here we have to differentiate, right? Because the volatility is sigma is already we have assigned. So let's assume a nu as a volatility here. So the uncertainty is following a random variable, or probably let's put this is some nu. So this I'll call it as a nu bar, and this let me put lambda. So just for a notation perspective. So I am saying random barrier is this T. So this being the mean and the lambda being the standard deviation for the same. So we have to get the volatility, we have to get the drift rate, everything remains the same. So initially we'll take the drift rate to be 0, right? The drift rate here we are taking it as 0. So which means I can very well take the value of the asset at any point in time as the value of the stock, yes, plus the uncertainty part. So the uncertainty part, I am taking the mean of that uncertainty part multiplied by D, that is, so uncertainty in the recovery value, I am taking the mean, so that much I am able to recover in case of a default times the total value of the debt. So this is what I am calling it as the total value of the asset. Now the same way if I am looking at the volatility of the asset, again I am going with the equity volatility. So the equity here, let me call it as E only, ET. So equity volatility is ET. So earlier in the Merton model also we had sigma E times ET is equal to sigma times AT times ND1. This is what we had. Now here also I can say sigma E times the value of equity is nothing but the value of the volatility of the asset and the value multiplied by the value of the asset. What is the value of the asset now? It is the value of equity plus the randomness in the uncertainty times D. So the gamma times D is what, or pi times D is what I am typically considering as the value. The volatility of the equity comes out as the volatility of the asset multiplied by the value of the asset, where pi is a random variable, divided by the value of the equity. So that is what we can derive for the volatility of the asset. And I can also go ahead on the same line with the probability of, so here we have another scenario, probability of survival to time t, which we are talking of n of minus, here I'll define something called alpha t by 2 plus log d by alpha t. We'll define what alpha and log d's are, minus d times n of minus alpha t by 2 minus log d by alpha t. So this is what we are defining as a probability of survival. The d, which is the kind of cutoff point which we are trying to look at, is coming out as S plus the E, which is the value of the equity plus pi times the value of debt, the average value of the uncertainty coefficient by pi d, pi bar times d, e to the power of lambda square, which is the variance. And similarly, the alpha t comes out as the value or the volatility of equity times the equity value divided by the asset value, which is E plus pi bar times D squared T plus lambda square. So this is what is coming out to the value of the alpha. So we are having alpha t, we are having d, and based on this we are coming out with the probability of survival. So this you can very well model going with the credit grade matrix. The same thing if you model in your spreadsheet. This is what tell you the probability of survival, and 1 minus of that will give you the probability of default. So when I'm talking, so this entire thing is modeled with respect to the number of shares. So I'll take both the common shares as well as the preference shares. So I'll have to compute both of them. Then I am also talking about the debt per share. Everything is per share basis. So here we are looking at the total liabilities. When I have to compute the debt per share, I am taking the total liabilities and I am dividing it by the total number of shares. And here I have to differentiate this concept of debt for financial firms versus non-financial firms. So in case of non-financial firms, right, when I'm talking about the financial debt, I'm looking at the short-term borrowings, long-term borrowings, plus half of all other short-term liabilities and long-term liabilities. Total other short-term liabilities and long-term liabilities I am considering in this way for a non-financial firm, whereas for a financial firms or companies having large subsidiaries or probably for some kind of banks, I can very well eliminate. This is what is being suggested through the model. I can very well eliminate the short-term borrowing, right? But this is a one way of finding out what is the financial debt. So this financial debt is something that we are covering, and then we have to find out the recovery rate. The recovery rate, the mean of it we said is 5R, and we have taken the volatility of the recovery rate as lambda. So these can be variable, but typically the mean is taken, let's say around zero point 0.5, and the standard deviation is taken to be around 30%. Or you can very well estimate the standard deviation based on the implied volatility of the option or the historical volatility of the underlying. I can very well take and use that as the volatility of the uncertainty as well. Now all these things can be taken into an Excel spreadsheet, which can help us in terms of finding out what is the probability of default associated with the same rely. Right? So let's try initially to start with. So if I am talking about with respect to the recovery mean, I'll for time being assume it as around 0.5, 50% can be recovered on an average, whereas the standard deviation, volatility of the recovery, volatility of recovery, I can very well take it to be around 30%, which is the lambda, right? And let's look at the time to default or time, whatever the time period which we are considering or evaluating the default is 1 year, right? The time horizon for which we are doing this model, I can very well assume it to be 1 year. Then we'll try to get some information from the balance sheet of the company. Some of the important things that I require, this is a non-financial firm, so I require short-term borrowings, I require long-term borrowings, I require other short-term liabilities and other long-term liabilities. So these four I require for this company. So let me go back to their annual report. Alright. Okay. So this is their balance sheet. Long-term borrowings 76,227. The long-term borrowings is 76,227. All right. So other non-current liabilities is the remaining part. So 90,308 minus this one. So I'll take it as 90,308 minus this number. I'll take them as other long-term liabilities. Similarly, short-term borrowings 12,914. So other short-term liabilities, I'll take it as 91,301 minus the short-term borrowing. So these are what are the numbers that are working on. So the balance sheet information which is needed to calculate the financial debt, I have taken all these things. And if at all they have some preferred equity or which is the preference shares, if at all they have any, I can capture them. And I would also like to look at if there is any kind of a minority interest, especially when I am looking at on a consolidated level, there is a possibility of the minority interest as well. So in here we don't have any kind of preference share, so I'm not bothered about, and even the minority interest is not existing here. So I'm not considering those things also. So we have already said the financial debt. So using this, I can go ahead and do the computation of the financial debt of the firm, which I add up the short-term borrowings and the long-term borrowings, but only the half of the other short-term and long-term liabilities. So I'll take short-term borrowings, I'll take long-term borrowings, plus only half of the other short-term liabilities and long-term liabilities. So this is telling me that the financial debt of the company is this much. And if at all I am looking at a minority interest and all that stuff, I can very well look at from this, I take out the minority part of it. So because the minority part does not exist, so I can very well keep the debt to be as good as this minus the minority part. So this is the amount of debt that is existing. Now I also need to compute the total number of shares, right? So I need to get the total number of shares. So share related information I need to capture. So we got the total number of shares in crores, right? Number of shares, we got it in our earlier video, 3236 crores. So here I could look at the share capital part issued, right? 3236 crores is the total number of shares that they have issued. No preference shares. So these are the total number of shares, right? So this can help me in terms of computing the debt per share, which can come out as this number divided by the number of shares, working out to the debt per share. That's one information. Volatility, either I can take the historical volatility or I can go with the option based implied volatility, whatever it is. So if I go with historical volatility as the volatility for the process, so I'll take the standard deviation associated with the log returns, multiply it with the square root of the number of trading days in the year. Okay, so 27.39% works out to be the historical volatility. And during this period, I can very well find out the risk-free rate. I will take it as 7.25%. So even that is fine, right? Now we got the debt per share. So we have computed we have got the number of shares, and the debt per share is computed. Even we got the volatility. Here in this case I have used the historical volatility, but you can very well use the option based volatility as well. Now I need the asset value. Right now I need to compute the actual credit grade related calculations. So I require the asset value, which goes as the equity value. The way we are getting the asset value is the equity value, which is the number of shares multiplied by the share price, plus we have lambda, the that pi bar times the d. So that's what we will compute. The equity part is the number of shares multiplied by the ending share price. This is the equity part, and the pi bar is zero point 0.5 times the value of debt we have already taken. This is the value of debt. So this is giving me that my asset value is this one. Now we had a few credit risk based, credit grade based parameters to be computed. One is the D. D we have used the formula earlier. The D is coming out as S plus pi bar D by pi bar D into e power lambda squared. So this is what we are computing. So which works out as S or probably E. Sometimes we call this E. E is nothing but the value of equity. So I'll take this multiplied, probably let me have one equity value directly. So which is nothing but the number of shares multiplied by the latest share price. So this is giving me the value of equity. So here I'll use it as the value of equity plus pi bar d, which is nothing but I can take either this again, pi bar times d. So the d, okay, here equity also we can take per share, right? It would be better if I take the equity per share itself. That would be simpler for us to operate. Even the asset value, I'll take it as per share only. So when I do this, the asset value also per share, I'm taking the stock price per share. So equity value, I'll say per share only, wherein I can directly use this last day's information. So this is the equity value per share. So here I'll do the asset value as equity value per share plus pi bar times the debt per share. So I'll take this. So this is coming out to be my asset value. The D also I'll go with equity value per share plus pi bar times the value of the debt per share. This divided by pi bar times D. So I'll take pi bar times D. D is debt per share, and this multiplied by e to the power of lambda squared. Lambda is the volatility of the recovery value. So which is giving me that my D is some 54, and similarly I can find out my alpha T squared. Right, alpha T squared also I can very well find out. Alpha squared. Right, let's find out alpha squared as well, which comes out as the equity volatility. The equity volatility, I am taking the historical times the equity value per share, which is this one, divided by the asset value per share. So this is my asset value per share. Did I take it? So probably I can take it as equity value plus the debt value, right? Or we have asset value per share is what we have. So this entire thing I'm taking as a square. Along with that, I'm also adding the volatility of this. So basically it's like, if this is not volatile, my alpha squared is exactly going with this formula. If you look at it like this, let me put here. See, we know that it is sigma E times ET is equal to sigma times AT times ND1. So from here you will get the sigma E is always sigma squared sigma AT ND1 by ET. Now if I want the square of it, it's going to be something like this. Or similarly, if I want sigma squared, I can take it as sigma E squared ET squared divided by AT squared ND1 squared. Now ND1 is more and more in the Merton formula associated with the probability of exercising the option. Now here the same logic, if the lambda is volatile, I have to add even that component as well. Now to add that particular component, so that's the reason if I'm talking about the volatility associated with the overall asset, I'm taking equity volatility multiplied by the equity value squared divided by the asset value squared. But along this is multiplied by T, and this I am adding up the volatility that is associated with the uncertainty random variable. This is per period, so I am multiplying it by T. So that is what is going as a part of our computation. So this squared times T, the T in this case is anyhow 1 year. So this is giving me, this is by alpha squared. Right from this, if I am getting my alpha, it's nothing but, if I am getting my alpha, it's nothing but the square root of this. Right, so this is the alpha that I am getting. Now from here I can very well compute the probability of survival, for which also we have a formula. The probability of survival is given through the norms dist, right, minus alpha by 2 minus alpha by 2 plus log D divided by alpha. Log D divided by alpha minus D times the same norms dist minus alpha by 2 minus log D divided by alpha. So this is what is an expression given by credit rate. Okay. So this entire value comma 1, even here I have to give comma 1. So the probability of survival is coming out very close to 1. Right, very rare that it is going away from there. The probability of survival is close to 1, which means the probability of default is 1 minus of this. Now here also we can very well try out just playing around with a very small equity value. Let's say the equity value per share is nowhere there, it's let's say around 100, or probably it's around 30. Yeah. Now if the equity value per share is going close to 30, we are seeing that there is a probability of default, right? If the equity value per share is 50 also, the probability of default is very, very minimal. So if the equity value goes to 70, almost kind of shielded. So that's the way, right? So we can very well look at all these calculations, and based on that we can try to find out at what rate the price has to fall so that the company will go into default kind of stuff. So this is the credit grades based model, which is also a structural model, which is taking the data from the balance sheet of the company, and based on which it is able to compute the probability of default and survival of the company, right? I hope you got some amount of key information with respect to finding the probability of default through the credit grade model through this. If you have any further queries, you can very well get back to me by giving me a call on the number that I have shared below, or you can send an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.